Hello, so I've decided to make a little devlog on some simulation software I'm developing. I'm trying to make right now it was brought to my attention that there is no good simulation software for equilibrium chemistry. So like there's no good FET for forever for equilibrium chemistry, the forward rate, reverse rate, and whatever. Um, there's apparently no good visualization for that, not FET, not anything. So I've taken it upon myself to try to bring this to the world. So right now, I just started working on this today. It's not very well developed, but I've done a little bit so far. So here, let me just show you. So what we have here, this is made in Python with Pygame, by the way. But we have a bunch of atoms over here that are bouncing around with kind of pseudo Brownian motion. I think, no, it's actual Brownian motion. I generated some Brownian motion for them. And it's really hard to tell because they're bouncing around so fast. But yeah, like see that one, there's a yellow circle, which is just, one big atom, like I don't know, if it's HI, that's iodine. And then we have those black atoms, which are smaller atoms, the hydrogen, I guess. And then we have the combined atoms, which I don't know if you could see. There was one. There's one right there as well, which is like the combined HI. So small is the black one, big is the yellow one, double is the double one. And this is just kind of tracking their concentration right now. So like they're both fluctuating about the equilibrium point, because right now the rate law is set up as such. I'm sorry if this is killing the bit rate, by the way, but it is what it is. Here, let me actually slow it down really quick. So velocity, speed, scale. Where is it set? Here it is. Let's just slow them down to 0.1 speed. It's just a visualization right now. It doesn't actually make a difference. Yeah, and they'll speed up in a second after. Let's do half speed. Anyway, I've gotten sidetracked by trying to make it look nice. But anyway, so if you notice over here, they're going to start fluctuating about the equilibrium point, which is just 250, because there's 500 total. There's 500 of each. There's 500 of each small and big atoms. So that means they fluctuate around 250 for the equilibrium point. That's just the rate. Right? Because the rate constants right now for each are just 1. That's just how I have it set. You can change it though. And I can destabilize the equilibrium here by either pushing the reaction forward or backwards. So this will instantly make 100 big atoms, or 100 double atoms. And this will instantly dissolve 100 double atoms to destabilize that. So if I push it forward, see that jumped up, and now it's going back to equilibrium kind of slowly. Right? If I push this backward, it's going to again go back to equilibrium. And if I push it forward really far, you can see it goes back to equilibrium much faster, because and then you can see the double atoms there. And this is actually an accurate reflection of what's going on. This is a real accurate reflection. And if I push it backward really far, you can also see what's happening there. So what's cool, and it'll slowly go back to equilibrium in a second. The cool part is, because of the way I have it set up, you can go up here to wherever this is set up, and you can actually change the K. So this right here is basically the rate laws, and the forward rate is making the big double atom, and this is the reverse rate is dissolving them. And you can say, okay, well, I want this reaction to heavily favor products. So the K for the Kc is products, K forward minus K backward. So our K is going to be 5, and this is going to favor the reactants. Favor the products. So now we run this, and we'll see that's reflected on the concentrations. You'll see the equilibrium point has shifted, and now the equilibrium point is where there are more double atoms instead of single atoms, right? And if I destabilize it, it'll go back to that equilibrium point, and if I push it back, it'll go back to the other equilibrium point as well, right? I can also make it instead favor product, or no, I cannot speak. Favor the reactants. Yeah. So this should favor the reactants. This favors the reverse rate. And now, so now you can see that the rate is heavily favoring the reactants. So yeah, there's that. There's that. This probably won't work with the real numbers just because of the just the way I've set it up. But it works. It's a technically accurate demonstration of a first order synthesis equilibrium reaction. I think that's what they're called. Whatever. But I plan on making this user interface look a lot nicer. This is basically a developer's testing thing. I know it looks bad. I haven't had time to really work on the looks. I'll plan to have like some graphs of the concentration over here, some other stuff like that. I might be able to like implement heat and see how that affects like this concentration change over here. Whatever, but I think there's some serious potential here. Anyway, that's it for now. But thanks, and I hope you enjoy. Let me know if this is something that you'd like to see, or if you'd be interested in this at all.